A primality test is an algorithm for determining whether an input number is prime. Amongst other fields of mathematics, it is used for cryptography. Unlike integer factorization, primality tests do not generally give prime factors, only stating whether the input number is prime or not. Factorization is thought to be a computationally difficult problem, whereas primality testing is comparatively easy. Some primality tests prove that a number is prime, while others like Rabin prove that a number is composite. Therefore, the latter might be called compositeness tests instead of primality tests. Simple methods. The simplest primality test is trial division. Given an input number n, check whether any prime integer m from 2 to shn evenly divides n. If n is divisible by any m, then n is composite, otherwise it is prime. For example, to test whether 17 is prime, test whether 17 is divisible by 2, or 3. Since a prime is only divisible by 1 and itself, if we reach 3 without finding a divisor, then we have proven that 17 is prime. However, we don't actually have to check all numbers up to n. Let's look at another example, all the divisors of 100, 2, 4, 5, 10, 20, 25, 50. Here we see that the largest factor is 100 halves equals 50. This is true for all n, all divisors are less than or equal to n/2. We can do better though. If we take a closer look at the divisors, we will see that some of them are redundant. If we write the list differently, 100 equals 2, 50 equals 4, 25 equals 5, 20 equals 10, 10 equals 20, 5 equals 25, 4 equals 50, 2, it becomes obvious. Once we reach 10, which is, the divisors just flip around and repeat. Therefore, we can further eliminate testing divisors greater than. We can also eliminate all the even numbers greater than 2, since if an even number can divide n, so can 2. The algorithm can be improved further by observing that all primes are of the form 6Ka plus or minus 1, with the exception of 2 and 3. This is because all integers can be expressed as for some integer k and for I equals a 1, 0, 1, 2, 3, or 4. 2 divides. And 3 divides. So a more efficient method is to test if n is divisible by 2 or 3, then to check through all the numbers of form 6Ka plus or minus 1. This is 3 times as fast as testing all m. Generalizing further, it can be seen that all primes are of the form ck plus I for I.